Right, so I'm going to explain the vector product, the cross product today. Okay, so we have, inner product. So for the vector multiplication, we have, two kinds, right? The first kind was inner product. The result of the product is the scalar, the number, right? That's the inner product. But we have the other one, which is vector product, and it's called cross product because it is cross there, right, between two vectors. And this one result in a vector, not number, right? This multiplication result in vector, v. Okay. So v, to be a vector, it needs to have length and direction, right? So length we define as the area of the parallelogram between the two vectors. Okay, A vectors, B vectors. The inner side of this really makes the parallelogram, okay? This one. And the area is the length of V. Okay? This length of V is the area of this parallelogram. Okay? And we need direction. For direction of V, we decide to have and follow right-handed rule. Okay? So if you have a right hand, the thumb is directing A, and the directing finger is B, and middle finger is V. Okay, if it's orthogonal each other, right? 90, 90, 90 each other. If it's hard for you to memorize, you can find this screw rule. Okay, right hand screw. So it's like from A vector to B vectors. It's just moving that. Rotating that way, and this is thumb is the direction of V. Okay. The component wise, the calculation this. So V is A cross B, and you put determinant calculation I, J, K. You remember Wronskian. Okay. So the standard basis, you put standard basis. And you put components of first vectors, okay, A1, A2, A3. And you put on the third row, you put components of B. Okay? The calculation, you first I times the cofactors of, this matrix that eliminates, the selection, right? And minus J, so this one, right? K, so this part, okay? And that's the component. All right? Properties of vector product. You could place a number in anywhere in the cross product. Okay? That's the same thing. And cross product is distributive. Okay? And this is actually symmetric or commutative, right? But this is anti-symmetry. Okay? Anti means its counterpart. Okay? Its counterpart is if you switch the position of the cross product, that introduces minus. Okay? So that's a counterpart of switching the position of vectors. And the fourth one, that's definite, right? Because of the determinant calculation, you cannot associate like that, right? So no associative or not associative. Okay. Let's take an example. Simple example. Where is it? Okay. So vector B is -2, 3, and 0. C is 2, -4, -1. Okay. And D, 3, -1, and 5. Okay. Then what is B cross C dot product D? Okay, so B cross C dot D is ijk minus 2, 3, 0, and 2 minus 4 minus 1, right? And dot product with 3 minus 1, 5. Okay? So that's, you pick I times 3, 0, minus 4, minus 1, right? Minus J, minus 2, 0, 2, minus 1, plus K, minus 2, 3, 2, minus 4. Okay? And dot product with 3 minus 1, 5. Okay? So that's minus 3, and that's minus 2, and that's 8, minus 8 plus minus 3, so it's I'm sorry, this is 8 minus 6, so it's 2. And dot product with 3 minus 1, 5, that's minus 9, plus 2 plus 10, which is 3. Okay? All right. Okay. For the factor product, we have one last, one more product. Okay? This is not used frequently, but, sometimes it is used. Okay? So we have triple product. So far, inner product and vector product is between two vectors, right? But we can define one more product, triple product. Okay? But triple product gives scalar. Okay? This result is a number like inner product. Okay? And you write this way. So 3 vectors is placed that way, and it is defined that way. So you have to do the cross product first, and then the inner product. Okay? Then this one is special in this way. Otherwise, it's I, J, K. It has to be, right? But instead, A becomes kind of basis. It acts like a basis. Okay? So it's it's scalar at the end. Okay? And this property, you can, put A cross B here.